Here, have a nicer, that one's nicer than the top one. Top one gets like scrunched as I go. All right, so we are starting compound interest, which is, pardon the pun, when things get interesting. All right, so I won't really do a review because we finished simple interest, but as we go through and introduce things in compound interest, I'll kind of highlight how things have changed from simple interest, right? So remember, from now on, right, we're just building on concepts that we've already learned, right? So we learned simple interest, how that behaves, right? That's actually kind of rare that we have simple interest in real life, but it helps us build these solid building blocks, things like drawing a timeline, right? Those skills are really important for us to have now when we go into compound interest. The ideas don't change, right? We deposit some money, it sits there, and at the end we have some more money, right? So that idea doesn't change, but but the calculations change a little bit. All right, so we are starting chapter 5, which is compound interest. And if you look on your formula sheet, right, we finished simple interest last day, and then now we're moving into compound interest. We're going to have like the interest is going to be compounding for the rest of the course, right? But this is the section that we'll call compound interest. Yeah? So that can be a little bit finicky wording wise, but it's fine. Let me just center this a little bit more. Okay. As always, section 1 of all the chapters, I feel like, is called the basics. So the basics, this is where we're gonna do a run through of everything that's new, but also making the connection to what it was in simple interest, right? So first, let's talk about what compound interest is. So compound interest is, kind of neat, because with simple interest, right, we deposited some amount, and then it wasn't until the end when we took it out that we had the principal and the interest, right? Now with compound interest, there's going to be some interval where we get the interest and it gets baked onto the principal amount, and then we earn interest on not just the principal amount, but also the little bit of interest that we've earned up to that point, right? So at certain kind of stopping points, right, if we're compounding quarterly, for example, then 4 times a year it stops and says, how much interest have you earned until this date? I'm going to add that onto your principal, and then you'll earn interest on that lump sum, right? So it's compounding at some frequency. So compound interest is when we're making interest on our interest as well as our principal. So is when we're making interest on our principal investment as well as the interest earned until that point. Earned until that point. So what we're going to have, right, at some frequency, right, and that's going to be the compounding frequency, which we'll talk about, but at some frequency, right, it's going to, let's say the bank is going to stop and say, okay, how much interest have you earned? I'm going to tack that onto your principal. Now your principal is a little bit more than what it was, right? And now you can earn interest on that amount. And so at some specified frequency, the amount of interest earned is compounded, right? I'll just put in brackets added to, right? Compounded just means that you're pushing things together. So added to, added to. Sorry, the 2 wasn't meant to be in the brackets. Added, compounded, aka added to the principal amount. So the first thing that we're going to introduce, right, is a compounding frequency, because we've already mentioned it a couple of times. So let's just tackle that. So a compounding frequency is, of course, just the frequency. It's kind of self-explanatory, but the frequency that interest is compounded. There's no really better way to say it. That interest is compounded. Some common compounding frequencies that we need to know, right? So we need to know these frequencies because they're going to come up in questions. And if I say it's compounded biweekly, then you need to remember that that frequency is 26. So what I'm going to do is we're going to list all these frequencies, and you're going to have to memorize them somehow, right? Most of them are pretty straightforward, right? But some of them are a little bit tricky. So some common compounding frequencies we need to know are, and we'll kind of start annually, right? So every year, annually is once per year. I guess I forgot to mention it, but the compounding frequency is denoted by a lowercase f. So for annually, f is 1, right? Once per year. Semi-annually, I think you guessed it, is twice per year. And f is 2. Quarterly, which, I mean, in business we definitely use a lot. Quarterly is 4 times per year. So f is 4. It gets confusing because in a quarter there are 3 months, right? And so every 3 months we've got a quarter, but the frequency is 4. So that's where it gets a little dicey, right? But as long as you remember, quarterly is 4. quarter 4. Monthly, 12 times per year. So F is 12. Bi-weekly is the one that gets a lot of people. Bi-weekly, you just need to remember, bi-weekly is 26 times per year because it's every 2 weeks, right? And so F is 26. That one's kind of a sneak attack for many. And then we're back to the ones we know. Weekly is 52 times per year. So F is 52. And then we already talked about daily, right? We assume that a year has 365 days. So daily, 365 times per year. So F is 365. Those are the ones that you're gonna just memorize and know. So if I talk about, you know, compounding quarterly in a question, then you know what I mean. See you later. What is it? Outwit, outplay, outlast? That's you guys. I don't watch Survivor, but my husband does, and he loves it. So, but I can't remember what it was called. The Edge of Extinction. That's you guys. All right. So we've talked about the compounding frequencies, and so these compounding frequencies are going to change the way we look at time, right? Because time, for simple interest, we used to talk about time in years, right? But now our time is going to be the number of compoundings, okay? And so for compound interest, we use the number of compoundings instead of time, right? So on our timelines, the length of the arrow will be the number of compoundings. Some notation, right? The number of compoundings, or I guess, sorry, I should put it here. The number of compoundings is denoted by a lowercase n. So n is the number of compoundings. Sometimes it's easy enough to say, okay, well, you invested it for 2 years and you're compounding quarterly. Okay, there must have been 8 compoundings, but it's not always that simple. And so I always just use the formula that n is time times the frequency. And this is actually on your formula sheet, so I'm gonna box it up here. So n is the number of compoundings. T is still time in years, right? So that's the same as in simple interest. We use the same notation. T is the time in years. So remember before, if I told you, oh, you invested it for 4 months, you had to use T equals 4/12, right? Because you still had to convert it to years. We still have to do that for T, but now we're adding this extra component, right? So we're always just building on what we learned. And F is, of course, the compounding frequency. So in simple interest, right, we had R was our simple interest rate. So now with compound interest, we're gonna need to talk about our periodic interest rate. Okay? And so now, I'll just phrase it kind of the same way. So for compound interest, we use the periodic interest rate instead of the annual interest rate Annual, or I'll put in brackets actually, we could call it nominal. I don't think I've called it that before, but now we might see that in problems. So I just want to highlight that the annual interest rate or the nominal interest rate is just that R that we were using in simple interest. And so instead of the annual or nominal interest rate, which was a lowercase r, we used in simple interest. The periodic interest rate is denoted by a lowercase I. And what we have on our formula sheet is that I is R over F. And that's on our formula sheet, so I'll just put a box around it, right? And I'll just highlight what these things are, where I is the periodic interest rate. R is the annual or nominal interest rate. Annual/nominal interest rate. And F, again, is that compounding frequency. Compounding frequency. Just as a quick example, if the annual rate is 6%, compounded quarterly, what's the periodic interest rate? Compounded quarterly, what is the periodic interest rate? We use I equals R over F, right? I is the periodic interest rate. R is the annual interest rate. So that's going to be 0.06 divided by F, compounded quarterly. So I'll just highlight here that quarterly means that F equals 4. And the 6% means that R is 0.06. .06 divided by 4, we get 0.015. So the thing about compound interest is we don't get 6% every quarter. We get 6% split up evenly amongst the quarters, right? But because we're baking them together, at the end of the day, it's going to be a little bit more than 6% just over the year, right? Because we're compounding and we're adding a little bit more to the principal after each compounding. So the formula that we use for compound interest problems, so for compound interest problems, we use the future value is the present value. Now we denote it by PV. If you have a look at your formula sheet, right, for simple interest we use P, but for compound interest we use PV. And I talked to Stephen, and it has something to do with, well, principal amounts, you can't just stop at any point. Anyways, I said, yeah, sure, okay, whatever. We use PV for compound interest, but they mean the same thing. It's the original amount, or the backtracked amount, if you will, times 1 plus I to the power of n. Now, we've got a lot to get through today, but usually I show the derivation, but it's in the textbook, right? But it has to do with, okay, so we invest some amount, and then after each compounding, we stop and multiply the present value by 1 plus I. And we do that for n compoundings, right? Multiply by 1 plus I, multiply by 1 plus I, and then they all get put together to make this formula, right? And so if you're interested in where it came from, it is in your textbook, don't worry. But we're gonna skip that part for today. But here is the meat and potatoes of this whole section. The future value is the present value times 1 plus I to the power of n. Similar to the simple interest, right? But now we got I and n that we have to deal with. Okay. So one thing that I want to make clear is that your questions are still going to give you the annual rate. So they're not going to give you the periodic interest rate. That's going to be your job to find that. So that's an extra step with compound interest. And it's still just going to give you the time in years or something like 14 months. You have to convert that to years and then convert it to the number of compoundings, right? And so it's got this extra step where you have to find the periodic interest rate and the number of compoundings, right? But the information that you get is going to look similar to a simple interest problem, right? Except you'll have compoundings, so you know it's compound interest. But first, let's talk about, so where FV is the future value, PV is the present value, I is the periodic interest rate, which we said I is R over F, and N is the number of compoundings, N is time times the frequency. The problems that we have to solve, the problems that we will need to solve, oops, it says solve. We'll give the nominal rate, right, that annual interest rate, we'll give the nominal rate, the compounding frequency, oops, compounding frequency, and the time, right, in years. I'll put years in quotes because same way that you got time in years for simple interest, right? I could have said 14 days. Then you know T is 14 over 365, right? So time is still going to be in years, just like simple interest, right? So the problems that we'll need to solve will give the nominal rate, the compounding frequency, and the time in years. And before we do any calculations, we'll need to find I and N, right? The periodic interest rate and the number of compoundings. So, and before we do any calculations, we will need to calculate I. I'll put in brackets the periodic interest rate. And N, the number of compoundings. Yeah. Any questions so far? No, we haven't done anything. Maybe. I don't know. How about we do something? Section 5.2. So just like we did before with simple interest, right? I gave you the formula just like I did now. And then we went through and we looked at solving a problem, solving for the future value, the principal amount, R and T before for simple interest. We're going to do the exact same thing for compound interest, where we look at a problem where we have to solve for the future value and then the present value and then I and then N, right? So, but we'll start with present and future values. Actually, we'll start with future values. So remember that FV is PV times 1 plus I to the power of N. Okay. So solving for the future value, we'll do example 174. I'll just highlight just to separate them. But we'll do example 174. Where are we here? So this is kind of our first look at a compound interest problem. All wonky. we're going to keep all those things that we learned in simple interest, right? So we're going to keep building timelines. These timelines are just going to change a little bit, because instead of having T and R, right, now we're going to have N and I, because that's more important for solving these problems, right? So we're going to put N and I on there instead. But really nothing else changes. The setup of the timeline doesn't change, right? So the concept of the timeline doesn't change. So we want to know, what's the value in 10 years of a $150 deposit at a bank, surprise, surprise, which earns 6.8% compounded quarterly. Yeah. So let's just go through and figure out what we have here and map it out on a timeline. Granted, it's going to be a very simple timeline, right? Because we just deposit some amount and find some future value. But we're given, the first thing we're given is that T is 10 years. The initial deposit, that's the present value, right? So that's the initial amount. Remember, in terms of your timeline, the present value is always on the left-hand side, and then it grows to the future value. Opposite way for you guys, but. And so the present value is $150, which earns 6.8% compounded quarterly. That 6.8% is still R, right? So that's what I mean. These problems are still going to give you R and T and a compounding frequency, and you have to take those to find I and N, right? So R is 0.068, and then compounded quarterly, and so F is 4. Okay. So in terms of our timeline, right, we don't have dates, specific dates, but if we just say that this is today and this is at 10 years from today, or it doesn't matter when it is, then we've got a present value of $150, which is going to grow to some future value, the exact same way that we drew it for simple interest. Right? But now on the arrow, and it's nice because we've got lots of room, right? On the arrow, we're not going to have T, we're going to need to have N, the number of compoundings, right? And so what I like to do is just on the arrow, assuming I have room, I just do N equals time times the frequency, and then I can just calculate it here on the arrow. So N is time times the frequency, which in this case, T is 10 years, times the frequency, which is 4, which means we have 40 compoundings. This is one of those scenarios where, yeah, you could probably just have known that N is 40, but just like with these simple timelines, it's good to get in the habit of just being able to tackle any kind of problem, right? So if it's simple like this, or if it's more advanced, then as long as you get in the habit of just showing your work for calculating N, then you can do it for any N, right? Not just simple 10 years compounded quarterly, right? So that's why we do it for just even these simple ones. Shouldn't say simple in compound interest, should I? Anyways, same with R. R kind of was, we usually just put it on the side, right? And so same thing with a periodic interest rate. I'm just going to put I is R over F. Usually I like to stack my equal signs, but what I find with I equals R over F is I usually just do it across to save room for my the rest of my work. And so I know this is a no-no in math when we kind of list our equal signs like this. We want to stack them, but sometimes we don't have space. So that happens too. So 0.068. I know what you're thinking, but you just did that for n. That was different. 0.068 over 4. All right. Just take your annual rate over 4, the compounding frequency. And so 0.068 divided by 4. So each quarter, we get 1.7% or 0.017. Okay. So now, that's our complete timeline. Because we've got the future value isn't filled in, right? That's what we have to solve for. We kind of knew that because that's the example that we're doing, right? Solving for the future value. But even from the problem. So we use future value as the present value times 1 plus I to the power of n. We're solving for the future value, and the present value was 150. So now that we've done our fancy timeline, right, it's just a matter of plugging things in because we've done all the groundwork. 150 times 1 plus 0.017 to the power of 40. Right, n is 40. Okay. You have to be really careful with your BEDMAS here, right? Brackets, then exponents, then multiplication, right? You have to do 1 plus 0.017, then to the power of 40, and then multiply it by 150. Right? And so I'll just show my work here to show you how the order it should be done. So I get 1 plus 0.017 is 1.017 to the power of 40. (1.017) to the power of 40. I've shown you guys how to do powers other than 2 on here, right? Use the y to the x button. So you have the base on your screen and then the y to the x button, which is above 9. It doesn't do anything to tell you that, hey, I heard you. But to the power of 40 equals, and you should get 1.962628571. I'll write that out so you can check. Is 150 times 1.962628571. And then I'm going to times that by 150. That's my final step. So my future value is $294, or I'll do the full amount and then in the next step, I'll round to dollars. How about 294.3942857. So the future value in money is $294.39. Any questions about that one? So you have that extra step of figuring out your I and your N, but then it's just a matter of plugging into the formula again. You're back on track. Solving for the present value. Oh, I said future value on here, but I meant present value. I'll clean that up. We'll do example 175, but first I just want to show you, because what's, I don't know, kind of nice, I don't think that you need the present value I and N formulas because you really only need the future value formula. The other ones are just the other things derived from the first formula, right? So I kind of like to have less on my formula sheet, and then I can find whatever I'm looking for. But it's nice because they're on here, so you don't need to know necessarily how to solve for things, right? But I'm going to show you, well, the present value isn't that crazy, but I and n are a little bit harder to solve for, right? So if we've got the future values, the present value times 1 plus I to the power of n, and we have to solve for the present value, well, we just divide both sides by 1 plus I to the power of n, right? And that's exactly what you have on your formula sheet. Right? So the present value is the future value over 1 plus I to the power of n. I'll highlight it to show you that it's on the formula sheet, but I can't remember if I highlighted the future value formula. Check it later. It's way back. Okay. So that's just how we're going to solve for the present value. Because you've got the present value formula, if the formula is on your formula sheet, you're free to just use it, right? So you don't have to show me how you got it every time. But if it's not on your formula sheet, then you have to show me how you got it at least once. Okay. Example 175. Oops. Compounded quarterly again. Boring. That's okay. It doesn't really change anything, it just changes your F, but how you approach the problem doesn't change. So, all right, so we want to calculate the original principal, so the present value, of an investment that pays $5,437.52 at maturity. So that's your future value. Over a term of 27 months, right? So T is going to be 27 months divided by 12, right? Because T still has to be in years. At a nominal rate, so there's that word, right? That's your annual interest rate, R, of 8.5% compounded quarterly. So because we're just new to reading these things, I'm just going to go through and list the things that we're given. And so we're given that the future value has to be 5,437.52. T is 27 months over, so we have to divide by 12. R is 0.085. And compounded quarterly means that F is 4. If we have to draw a timeline, it's not going to be that wild of a timeline here, right? But if we draw this on a timeline, then we've just got 2 dates to deal with. Let's say, just for simplicity's sake, that we start today, and then here's 27 months later. The amount that we have at 27 months is 5,437.52. We want to know, well, how much did you invest originally? And so we're gonna trace this back to some present value. Right, so if you're bringing the money back, it becomes a principal or a present value. Same idea. Now, instead of T on the arrow, we take it that one step further and we have to find N. And again, what I'm going to do is I'm just going to do the calculation for N on the arrow, right? assuming there's room. If there's no room, then you can do it on the side somewhere. But it's always nice if there's room to just use it. So n is time times the frequency. Time in this case is 27 over 12, and the frequency is 4. So if we do 27 divided by 12 times 4, we get 9 compoundings. And then the last thing that we do usually, we just write R for simple interest, right? We write R somewhere around there, but now we have to find I. And so I is R over F, which is 0.085 over 4. 0.085 divided by 4 is 0.02125. All right. Now we've got all the information from the question on our timeline, and so we're good. So now we can do our calculation, and we know, because we just showed it, but also from our formula sheet, that the present value is the future value over 1 plus I to the power of n. The future value is 5,437.52 divided by 1 plus I, which is 0.02125 to the power of n, which is 9. I'll extend that fraction a little bit. Again, you have to be really careful with BEDMAS, right? You have to deal with what's inside the brackets first, then do the exponents, and then do the division. So we've got 5,437.52 over 1.02125 to the power of 9. Again, I'm showing probably more steps than you need to. But it's just so when you look back, you can see the steps that I did. So plus 1, and then to the power of 9, I get 5,437.52 divided by 1.208338535. You don't want to lose any of those decimals because they're actually going to make kind of the big difference, right? And so if you have to store that number somewhere, or I like to use the second answer button, which is over the equal sign. And so what I'm going to do is I'm going to do 5,437.52 divided by, and then that previous answer equals, and I get 4,499.997179. So in money, we get 4,499. Oh, haha. Oops. I didn't round properly. And things just get out of control, doesn't it? Yeah. I was worried I did something wrong, but no. The 99.7 cents has to get rounded all the way up to 4,500 even. Any questions about that one? Okay. Then we just keep going. We're going to calculate, find I, and then we're going to find N. And then depending on what time it is, then I'll let you be free. How about that? So you guys are troopers. So section 5.3 is calculating the periodic interest rate. Calculating the periodic interest rate I, and the number of compounding periods, and the number of compounding periods N. If we have to solve for I, then if we look at our general formula, the future value is the present value times 1 plus I to the power of N. And we're solving for I, right? We're slowly going to unravel this. But like I mentioned before, the formula for I is on your formula sheet. So as long as you know how to derive it, right? But it's just good practice and good to have seen it. So we have to divide both sides by the present value in an attempt to get I on its own. And so we get the future value over the present value is 1 plus I to the power of N. To get that N out of there, right, the power of N means that we have to take the nth root of both sides. Which means that we're taking the nth root. So remember, the nth root, we do the square root, put the n in the hook of the future value over the present value is, I guess I'll show it properly, the nth root of 1 plus I to the power of N. But those are just going to cancel, right? Because the nth root we can rewrite as something to the power of 1 over n. Now we've got to the power of n times 1 over n, which is n over n, which is 1, so it goes away. That's why we use the nth root. And so we get the nth root of the future value over the present value is 1 plus I. I'm going to revolving door this, right, to get I on the other side, but also in that switcheroo, I'm going to subtract 1 from the other side, or from both sides technically. So I get I is the nth root of the future value over the present value, and then minus 1. Remember what I is. I is the periodic interest rate. These interest rates are going to be really small, right? Even 6% becomes 0.06, but then if we're compounding semi-annually, for example, becomes 0.03. So usually the future value over the present value, once we take the nth root, it'll be 1 point something something, right? That's why we have to take away that 1 to bring it back to size. And I see that a lot where people forget to subtract the 1 and it messes up all your answers, right? And so you have to remember to subtract that 1. Because otherwise it's like 103% instead of 3%, for example. I'll highlight this so that, because we're going to solve for I and then for N. Let's do example 178. skip that page break here. Okay. So $15,000 was invested for 13 years until it reached a value of $30,000. If interest is compounded monthly, what was the nominal rate of interest, right? And so what we'll find is that we'll calculate I, but that's only in an effort to get back to R, right? Because we want to be talking about the nominal interest rate. Just like the questions will give you the nominal interest rate, when we're solving for I, we'll actually be solving for R, right? So we use I as the gateway in either situation, right? But usually the answer that we want is R, right? The annual interest rate or the nominal interest rate. And so I'll do it as a little different colored note here. So we usually want to solve for R, but we will need to solve for I first. Then we can use the fact that I equals R over F to solve for R. Right? So we're just undoing what we usually do, working backwards. So for our timeline, right, we invested $15,000 and then 13 years went by and we ended up with $30,000. That sounds great. What R made that happen, right? And so for now, I can't have it on the same screen, but that's okay. I'm going to use the same method, right? I'll say today and then 13 years from today, because as long as the distance is 13 years, it doesn't actually matter. So today, and then it was 13 years, yeah. 13 years. And today, I put in 15,000, and then 13 years later, I get 30,000. Or maybe I should put it down a level, because I like to have my arrows kind of lofty, I guess. 15,000 grew to 30,000. It doesn't matter. As long as you've got an arrow going from 15 to 30,000, you're fine. On the arrow, right, we do N is time times the frequency. Time is 13 years. And then times the frequency, compounded monthly now, so F is 12. That's a new one. Doesn't change anything, but 13 times 12, we do 13 times 12. Nice, 156. And I'll just indicate that we don't know what I is, and that's what we're trying to find. Since we have the formula for I, we can just start there, right? Or if you prefer to start with the future value formula and just forget about all those other formulas, that's fine too, right? But I think a lot of people just like to plug and chug, right? Plug stuff in, calculate, move on. So we've got I, we said was the nth root of the future value over the present value, and then minus 1. And that's from your formula sheet. Oh, hey, I keep forgetting to box things up. But this is on your formula sheet. Okay. So we know the future value, we know the present value, we know n, so we know everything that we need in order to solve for I. And so here we go. So we've got the 156th root of 30,000 divided by 15,000, and then minus 1. That minus 1 is outside the square root. All right, so just be careful. Let's simplify 30,000 over 15,000 before we take the 156th root, right? And so 30,000 divided by 15,000 is 2, right? So we want to take the 156th root of 2 and then minus 1. How are you going to take the 156th root of 2? Well, you can rewrite this as 2 to the power of 1 divided by 156, and then minus 1. Don't forget that minus 1. Because just as a rule, you can rewrite any root as whatever's inside to the power of 1 over the root, right? That's how we do these weird roots. And so on your calculator, on your calculator, 2 to the power of 1 over 156, you're going to have 2 on the screen and then hit the y to the x button. And then I would put brackets around, right? You've got these bracket buttons over the 7 and 8. So bracket 1 divided by 156, and then close that bracket with the button, and then equals. You have to hit equals, otherwise it'll just show 1 over 156, which isn't what you want, right? And so we have 2 on the screen, the y to the x button, and then in brackets, I'm going to do 1 divided by 156, close that bracket, and then equals. And so I get equals 1.004453137. In our calculations then, we can replace the 156th root of 2 by 1.004453137 minus 1. So this is what I was talking about before, right? You have to have this minus 1 because otherwise you're saying, oh, every month you get 100.45%. That's some bad banking, or good banking if it's your money, but bad banking overall, right? And so this becomes 0.004453137. Your I is always going to be pretty small, right? Your periodic interest rate. Because interest rates aren't that big, right? 5%, 6%, 3%. Right? So now I is 0.004453137. We wanted the nominal rate, R, right? So now that we know I is 0.004453137, we can solve for R. Remember that I is R over F. If I know I and I know F, I can solve for R, right? And so just using the variables here, to get R on its own, I would have to multiply both sides by F. So then I get R is I times F. Or you could plug in the values and solve for R. It's the same thing, right? And so R is going to be 0.004453137 times F, which was 12, right? Thank you. 12. So make sure you keep all your decimal places, however you want to do it on your calculator. And then times 12, and you should have an R of 0.053437644. Therefore, the nominal rate was 5.34%, right? Converting it to a percentage, because if you left it as a decimal, that's fine. I'm happy with that, right? But usually when we're talking about rates, interest rates, we usually report them as percentages, right? You always just want to check, right? So kind of bring the common sense into it, right? If you find an R of 5.34, that sounds reasonable, right? It's always going to be kind of in that range, right? So on the lower end, right? And so you just want to double check, right? Does that make sense? An R of 5.34%? Yeah, sure, right? Sounds reasonable, because rates are usually, you know, less than 10%. Right? Unless you're a loan shark, then they're like 20%, 30%, but that's nasty. Any questions about that one? So when we're calculating I, we're actually going to be calculating R, so it's got that little extra step. Same thing for time, right? And so if we're solving for time, we're actually going to have to solve for N first. So in general, right, let's solve for N from the original future value, the future value. But like I said, like I keep saying, this formula is on your formula sheet, right? So knowing the derivation is not going to be a big deal, unless maybe for a bonus question. I don't know. I just write the tests, guys. Just because it's good to know this kind of stuff, but it's not, you know, make it or break it. 1 plus I to the power of N. So now if we're solving for N, remember if we have to solve something from the power, then we have to take the log of both sides. But in order to do that, we have to move the present value over, right? So that it's just 1 plus I to the power of N on the one side. And so we do the future value over the present value is 1 plus I to the power of N. I dare say this is the only reason we reviewed logs, so that we could solve for things like this, right? It's good for other stuff, and if you flip the formula sheet, yeah, it's going to come back up, right? But it's for this idea of being able to solve for N, which is in the power. So I'll just make a note here. To bring N down, I'll put down in quotes here. We take the log, but I use the natural log, right? And we use the natural log typically. Doesn't matter, you can use any log, but we take the log of both sides. Right, and then by the properties of logs, if we have a power, it can be multiplied down in front. So what I'm saying is that the log of the future value over the present value is going to be the log of 1 plus I to the power of n. But by the properties of logs, this right-hand side can be rewritten as n times the log of 1 plus I. And I'll just clarify by properties of logs, which we reviewed, I can't remember when, but it was a little bit ago maybe. And nothing on the left-hand side changed, so we get the log of the future value over the present value. Now we can solve for n right now because we can isolate n. So I like to have n on the left-hand side. So n is the log of the future value over the present value over the log of 1 plus I. Which, no surprise, is exactly what you have on your formula sheet. So I'll box this up. Let's do example 179. All right. So in order to save for college, sound familiar? You want to invest $10,000. Maybe not so familiar. I don't know about you, but definitely did not have 10 grand. And have it grow to 15,000. Wouldn't that be nice? If the rate of interest is 8% compounded semi-annually, how long will it take for this to occur, right? How long is it going to take for 10,000 to grow to 15,000 if the rate of interest is 8% compounded semi-annually? Okay. So, first I want to make a note, right? So, we usually want to solve for time, right? And so we usually, same idea as before when we had to solve for I in order to solve for R, right? We want to solve for time, but in order to get there, we have to solve for n, right? So we usually want to solve for time, right? T. But we will first need to solve for n. And then use n is time times the frequency, right? Because now we'll know n, we solve for n, and we'll know the frequency just from the question. We'll be able to solve for time, right? N is time times the frequency to solve for time. It's like the worst time to have class in this room. It's nice that the sun is shining and everything, but man, all the lights are out, all the blinds are down. Still can't see the screen. Okay, So just like when we're solving these problems, right, we have to find the periodic interest rate and find the number of compoundings. Same thing when we're working backwards. We've got that extra step for solving for time and the nominal rate, right? So just keep that in mind. All right, so let's make a timeline of this, right? And go from there. So you want to invest $10,000. Here's the pickle though, when we're drawing these timelines, we are trying to solve for time, so we can't actually put anything up top, right? But just as a reference point, we'll call this today. And then here's some unknown point that we want to solve for. Some unknown point where you're so rich with $15,000. So we had $10,000 to begin with, and like the question says, it grew to $15,000. And we don't know what n is, right? So I'll just do n equals question mark, right? And then I've got I is R over F. R was 8% compounded semi-annually. So remember, semi-annually means that F is 2. And so we've got 0.08 divided by 2, which is 0.04. So now our timeline's complete. There's no more information from the question, right? It's all mapped on here, and it's pretty clear that we have to solve for n, right? And then time, but let's get to work. So we know the formula from the formula sheet is n times is the log of the future value divided by the present value over the log of 1 plus I. So we've got the log of 15,000 divided by 10,000 over the log of 1 plus 0.04. Let's simplify inside the logs before we actually take the log. 15,000 divided by 10,000 is the log of 1.5 over the log of 1 plus 0.04 is 1.04. We've done it before, but on your calculator, right, you're going to have 1.5 on the screen, and then hit the LN button. And then equals just in case, right? Or even if you wanted to, I'm pretty sure, or even 1.5 ln divided by 1.04 ln, and then equals, to do the whole thing, right? So if I do 1.5 ln, which is on the left-hand side, right, divided by 1.04 ln equals Sure enough, I get the right answer. I get 10.33803,507. So just make sure, 10, yeah. But I did all of it. So 1.5, the log of 1.5 is 0.405465,108. Divide, and I'm going to store that in 1. And then 1.04, the log of that is 0.039220,713. And then recall 1 divided by the previous answer equals 10.33803507. One thing about n is that we can't, so just like we couldn't make 0.7 of a chair, right? So we had to bump it up. For n, we can't go 0.338 of a compounding, right? So even though we, like with proper rounding, right, we would round down to 10, but 10 compoundings wouldn't quite get us to the future value that we need, right? Because we get more money as we go, right? And so what we do is we need 11 compoundings, right? And so I'll just make a note here. This is important and it trips people up, so I'll put it in pink. We can't have 0.338 of a compounding so for n, or so when solving for n, we always round up, or we always need to round up to the nearest whole value of n, regardless of the decimal. To reach the desired future value. To reach the desired future value. So n is 10.33803,507, but we would need n equal to 11. Right? So your n is always a whole number, right? And regardless of the decimal, you're always going to bump it up, right? Bump it up to the next compounding, right? Because after 10 compoundings, you're not quite at that 15,000 that you need, right? 11 compoundings, you're going to be at a little bit more than 15,000, but that's better, right? So after 11 compoundings, we need to figure out what is this in time. So now we can solve for time, which is t, right? N is time times the frequency. If we know n and we know f, we can solve for t, right? So we can rearrange this and say, well, then t must be n divided by f. So t is 11 divided by the frequency, which was 2, right? Nice. So 11 divided by 2 is 5.5 years. what's confusing is we're allowed to have partial time, right? We're allowed to have 5.5 years, but we can't have 5.5 compoundings, right? So it's just n that we need to adjust, not time. So now we know that if we have 10 grand and we want it to grow to 15,000 and we can find an interest rate of 8% compounded semi-annually, it'll take 5.5 years for it to grow. Okay. Any questions about that one? Let's do the coolest part of this, dare I say, course? I don't know. Anyways, have you guys heard of the rule of 72? Maybe. So it's just a quick approximation for how long it's going to take any amount of money to double, right? So all you need to know is the interest rate. So if I tell you, oh, I'll give you 3%, right? What we do, the rule of 72, and this is just the kind of math magic. No, it's proven in the textbook, but we don't need the proof. We can just apply it. If you take 72 divided by the percentage that you're given, the interest rate, then that'll give you an approximation for how long it would take some amount of money to double, right? Whether that be $1 doubling to $2, right? Or whether it be 1,000 doubling to 2,000, it doesn't matter, right? Any amount to double, and it's called the doubling time. And so the doubling time is the rule of 72. We can use the rule of 72 to approximate, so it's not exact, but it is nice to be able to get kind of a quick estimate of how long things would take, right? Especially if you're at the bank and they're saying, oh, we'll offer you 2.1%, then it's nice to just be able to say, okay, well, I know 72 divided by 2.1. Well, let's do it. 72 divided by 2.1. It's going to take me 34.3 years for my money to double. Is that worth it? Is it not worth it? I don't know, right? That's up to you to decide, right? But so we can use the rule of 72 to approximate the time it would take money to double at a rate or at a nominal rate R%. Okay. So the formula is that the doubling time in years is roughly 72 divided by R as a percentage. Okay. And I know I've been harping on you guys. You always have to convert your interest rates to decimals. This is one of those times where we don't, right? We just keep it as a percentage. And so this is a rare instance where we need to keep R as a percentage. Yeah. So let's have a look at example 181. An investment of $15,000 needs to double. That's actually not information that we need, right? It's just extra information, because with the rule of 72, it doesn't matter what amount it is, right? But at a rate of 8% per year, roughly how long will it take, right? And so the doubling time is roughly, so do you guys know the squiggly equals approximately equal? I think I've used it a lot, but just realized I haven't actually told you what it was. Approximately equal to 72 divided by our percent. So in our case, it's 72 divided by 8%. 72 divided by 8 is 9. So it would take roughly 9 years. So imagine you're at the bank and they're saying, yeah, sure, we'll give you a rate of 8%. Then you can quickly sneak out your phone and say 72 divided by 8 is 9 years. Am I happy with that? Is that good for me, right? It depends on how much you're investing and how okay you are. But it's a good kind of gauge to say, okay, well, 9 years for this amount to double, that's good or that's bad, right? So, because otherwise it can be kind of tricky to figure out, well, what's a good rate? What's a bad rate? How do I decide, right? And so this is kind of the most, no, not the most useful, but the most fun, useful thing that you'll learn in this course, I think. And because it's so easy, that's also fun. Okay. Works for population growth too, right? As long as you know a rate, you know how long it takes for something to double. Okay. All right. You've done your time. We were meant to go through another section today, but you did it. So if you're doing that Moodle quiz for next Tuesday, there might be a few equivalent payments that you can figure out because you have all the tools, but we'll go through examples next day. And if need be, then I can move the due date to Thursday or something if you need a little bit more time. All right, but otherwise, see you Tuesday. Oh, any questions? No. Forgot to ask. Oh. Okay.